We all remember learning about the hard and fast rules of electricity in physics class, right? But what if? What if those rules aren't so rigid after all? Today, we're going to peel back the curtain and look at the real story of the current flowing through your walls, connecting what's in the textbook to what's in your outlet. All right, so let's just jump right in. We're going to start by poking holes in one of the biggest rules you probably had to memorize, Ohm's law. You know the one, V equals I times R. And the key thing they always tell you is that resistance, that R, is a constant. But is it? What happens when it's not? And to see where things get, well, a little weird, we don't need some fancy, complex microchip. Nope. All we need is something super simple. The tiny little filament inside an old-school light bulb. Believe it or not, it's hiding a pretty big secret. Okay, get this. Just look at the numbers for this one single component. At a tiny 1 volt, its resistance is sitting at about 8.3 ohms. But then we crank the voltage up to 5 volts, and boom, the resistance more than doubles to over 17 ohms. Now hold on a second. If you're sticking to a strict reading of Ohm's law, this just shouldn't happen. So what on earth is going on here? The answer, in one word, heat. It's all about the heat. As more current pushes through that tiny filament, it gets hotter and hotter. And when we zoom way in, down to the atomic level, that heat makes the whole structure of the metal, well, it makes it vibrate like crazy. The best way to think about it is like trying to run down a crowded hallway. Now imagine everyone in that hallway starts shaking and jumping around. It suddenly gets way, way harder to get through, right? That's exactly what's happening to the electrons. And that difficulty, that's increased resistance. So, there you have it. This is what we call a non-ohmic component. And here's the kicker. These things aren't some weird exception to the rule. They are everywhere in modern electronics. For anyone designing a circuit that needs to, actually work in the real world, understanding this is absolutely crucial. And this whole dynamic dance between voltage, current, and heat, it leads us perfectly into our next big topic, power. All right, so this idea that our electronics are always generating heat and using up energy, that brings us to something we can all relate to maybe a little too well, the electricity bill. Because that number that shows up every month, it's not random. It's a direct measurement of the power you're using and for how long. So first, let's get power straight. Power is measured in watts, and it's all about speed. It tells you how fast a device is gobbling up energy. Think about it. A 100-watt light bulb is just chugging down electrical energy way faster than, say, a little 10-watt bulb. But here's a really important distinction. The power company doesn't actually bill you for power. They bill you for energy. Energy is the grand total. It's the how fast, that's the power, multiplied by how long you used it. And for billing purposes, they have this special unit you've definitely seen before, the kilowatt hour. And it's actually super easy to figure out what things cost to run. Let's take a regular 60-watt lamp. Okay, so you leave it on for 5 hours. That's 60 times 5, which gives you 300 watt-hours. Now, to get to the magic billing unit, we just divide by 1,000. So that's 0.3 kilowatt-hours. And if your electricity costs, say, 30 pence per kilowatt-hour, that lamp just cost you 9 pence. And that simple math, right there, is why everyone tells you to switch to low-wattage LEDs. It makes a huge difference. Okay, but here's the catch. Not all that energy you're paying for is actually doing the job you want it to do. And this brings us to a concept that is, no joke, one of the most important ideas in all of engineering, efficiency. So what is efficiency? Put simply, it's a measure of how much useful stuff you get out for all the electrical energy you put in. It's the ultimate bang for your buck. Of course, in a perfect world, every device would be 100% efficient, but we don't live in a perfect world. In reality, some energy always gets lost along the way. Let's look at this electric motor, for example. It's pulling in electrical power, but it's only putting out so much actual useful spinning motion. So you gotta ask, where did the rest of it just disappear to? Well, you can see it right here. It was lost. It turned into wasted heat. That means this motor is only 70% efficient. And that wasted heat, it's not just about a slightly higher electricity bill. Oh no. For engineers, it's a massive, massive problem. Heat is the #1 enemy of electronics. It fries components, it makes things unreliable, and it can cause entire systems to just flat out fail. Figuring out how to get rid of all that waste heat is a constant battle. So you've got all this power, all this current, and all this heat just coursing through the wires in our homes. That sounds
kind of dangerous, right? Well, it would be, except we have protection. So let's talk about the silent guardians, the unseen heroes hidden inside our walls that are working 24/7 to keep us safe.
First off, why do we need to be so careful? Because it takes a shockingly small amount of current to cause serious harm. We're talking just 30 milliamps. That's tiny, 30 thousandths of a single amp. But if that little bit of current passes through your heart, it can disrupt its rhythm, and that can be lethal.
Now, to keep us safe, we have a few different gadgets, and it's really important to know what each one does. You've got your fuses and your MCBs. That stands for miniature circuit breakers. Their main job is to protect your stuff, your appliances, your TV, your computer. They stop them from getting too much current and overheating. But then you have the RCD, the residual current device. Its job is way more personal. It's designed specifically to protect you. It's looking for tiny, tiny imbalances in the current that could mean you're getting an electric shock, and it shuts everything down in a fraction of a second.
And of course, there are a couple of other really basic layers of safety we can't forget. First, there's earthing. That's basically just giving the electricity a safe, easy path to the ground if something goes wrong, so the metal case of your toaster doesn't become live. And then there's insulation. That's just the plastic coating on the wires. Simple, but it's what physically stops us from touching the dangerous parts.
Okay, so we've looked at resistors that don't follow the rules, we've broken down our power bills, and we've met the safety devices in our walls. So what does it all add up to? What's the big picture here?
Really, it all comes down to one thing. This stuff isn't just about passing a physics exam. These ideas, they're the bridge between the theory and the real world. They're what lets us understand, design, and, most importantly, safely use the incredible electrical world that powers everything we do, from the phone in your hand to the lights in your home.
And that's our deep dive for today. We'll leave you with this one last thought to chew on. The electrical world around you isn't static. It's a living, breathing, dynamic system. So the next time your lights flicker or you hear that click of a circuit breaker tripping, take a second and think about what we've talked about. What is your electrical world really trying to tell you?